What if the most elusive force in the universe held the secret to instant communication right across its unimaginable distances?
Hmm.
Today, we're plunging into a really mind-bending idea using gravitons, the hypothetical quantum messengers of gravity,
Right.
to potentially leapfrog the cosmic speed limit.
It's a concept that, yeah, it truly stretches the boundaries of our imagination. And at its heart lies some of the most profound mysteries in physics, really.
Definitely.
Our mission in this deep dive is to explore the scientific groundwork and, let's be honest, the admittedly far-out possibilities behind this whole notion of graviton-based communication.
Okay.
It's all sparked by a fascinating source we looked at exploring this very idea of graviton networks.
Absolutely. It feels like pure science fiction, doesn't it?
Yeah,
Like flicking a switch and instantly talking to someone light years away.
it does.
But as that source argues, this isn't just, whimsical thinking. It's actually grounded in our current understanding of the cosmos and the ongoing quest to unify its fundamental forces.
That's the key. It starts with real physics.
Okay, so let's really get into it. What exactly are these gravitons everyone's talking about?
Right, well, to get a handle on gravitons, we first need to take a quick step back. Think about the four fundamental forces.
Okay, the big ones.
Yeah, electromagnetism, the strong nuclear force, the weak nuclear force, and, of course, gravity.
Got it.
Now, what's really interesting is that for the first three, we know they have corresponding quantum particles that carry their influence.
Like messengers?
Exactly. Photons for electromagnetism, gluons for the strong force, and the W and Z bosons for the weak force. Think of them as the tiny workhorses, making things happen at the smallest scale.
Right, the microscopic delivery drivers for these forces. But gravity's always been the odd one out, hasn't
It
it?
has.
Einstein's general relativity paints this picture of gravity not as a force carried by a particle, but as the very fabric of space-time being curved, warped by mass and energy.
Precisely. And general relativity has been incredibly successful, explaining gravity on the grand scale, planets orbiting stars, how galaxies form, all that.
Yeah.
But when we try to merge that understanding with quantum mechanics, our best theory of the very small, well, things get very complicated.
Yeah, the classic problem.
Yeah, and this is where the idea of the graviton pops up within quantum field theory. It's proposed as this theoretical quantum particle,
Okay.
massless, with a specific property called spin 2, and it would mediate gravitational interactions at the quantum level.
So like the photon does for light.
Kind of, yeah. Similar to the force carriers for the other three forces, it would be the quantum doer of gravity, in theory.
Okay, in theory.
Yeah.
But the source material makes it clear. And there was that paper from, 2006, Rothman and Bahn.
That's the one. Can gravitons be detected?
Right. It really emphasizes this. We've never actually seen one directly, have we? It's still purely theoretical.
That's a crucial point to underscore, absolutely. Despite huge theoretical efforts, directly detecting gravitons experimentally is, well, it's proven incredibly challenging.
Why is it so hard?
The Rothman and Bone paper details the immense difficulties. It boils down to just how incredibly weak the gravitational interaction is compared to the other forces.
Weaker than electromagnetism.
Oh, vastly weaker. This inherent weakness just makes isolating and observing individual gravitons an extraordinarily difficult task with current or even foreseeable tech.
Okay, so we've got this theoretical particle, maybe the key to quantum gravity, but it's incredibly elusive.
Yeah.
Now, let's loop this back to communication. The source really focused on the frustration of the cosmic speed limit, light speed.
Right.
Why is that such a fundamental roadblock for, reaching out across the cosmos?
Well, if you connect this to the sheer scale of interstellar distances, the limits imposed by light speed become, frankly, staggering.
Give some examples.
Okay, well, the source highlighted this. Just sending a message to our own sun takes about 8 minutes.
8 minutes, okay.
To reach Proxima Centauri, our nearest star system, a beam of light needs 4 years.
4 years. Wow.
And if we wanted to talk to the center of our own Milky Way galaxy, we're looking at a light travel time over 20,000 years.
20,000 years. That really puts waiting for a reply all email into perspective.
Doesn't it? So if we ever truly aspire to explore and interact with the wider universe, this light speed barrier is a massive challenge for coordinating voyages, for planetary defense, for well, anything complex across space.
Yeah, real-time coordination is just impossible.
Exactly. And this is why scientists and thinkers have, for a long time, speculated about ways to maybe get around this cosmic speed limit, or at least find alternative ways for near-instant communication.
Faster than light or FTL communication.
Right. The source brought up quantum entanglement as one possibility.
Which has its own issues.
It does. And graviton-based signaling as another compelling, though, again, highly speculative prospect.
Okay, which brings us to the really fascinating part. How could we even begin to imagine using these theoretical gravitons to send messages across the vast emptiness of space? The source touched on some pretty wild hypothetical methods, right?
It certainly did. It delved into some incredibly imaginative theoretical avenues. One idea is gravitational wave modulation.
Gravitational waves.
Yeah.
Those are the ripples in space-time.
Exactly. Predicted by Einstein, and we now have direct proof they exist thanks to LIGO, the Laser Interferometer Gravitational Wave Observatory. They got that first direct detection back in 2050.
Straight from colliding black holes. Huge events.
Massive events. So the intriguing question raised is, could we, in principle, modulate these waves? Maybe at much higher frequencies than LIGO detects. Could we encode information onto them?
Huh. Like sending Morse code using ripples in space-time itself.
That's the analogy, yeah. But on a cosmic scale, sending information encoded in the very fabric of space-time. It's mind-blowing.
It really is. And the source also mentioned something about leveraging graviton interference patterns. What's that about?
That's another highly theoretical concept. It hinges on whether we could ever develop the tech to generate and detect individual gravitons.
Which we just said is incredibly hard.
Immensely hard. But if we could, maybe through some currently unknown quantum effects, or perhaps manipulating things like black hole analogs,
Okay, if.
then it's conceivable we could use their quantum properties, like their spin, that intrinsic angular momentum we mentioned earlier. We could potentially use that to encode information, a bit like how we use the polarization of photons' light particles to send data down fiber optic cables right now.
Ah, okay. So using a quantum property to carry data, similar to how we do it with light, that makes it slightly more tangible.
A little, yeah, though the how is completely unknown.
And then, of course, there's quantum entanglement. That always comes up in these discussions. Could gravitons themselves become entangled?
Theoretically, yes. Entanglement is that bizarre connection, right? Two or more particles linked, sharing the same quantum state, no matter how far apart they are.
Spooky action at a distance.
That's the famous phrase. There was a 2020 paper mentioned, Brahma and Yom, exploring graviton entanglement, especially regarding the black hole information paradox.
Okay.
So if gravitons could be entangled, it theoretically opens up a sort of non-local channel, a connection not limited by distance.
Instant connection.
But here's the crucial caveat. The current understanding, even with entanglement, is that you likely can't use it to transmit usable information faster than light.
Oh? Why not?
The correlation between entangled particles is instant, yes, but you can't control which outcome you get locally in a way that sends a deliberate message faster than light. It seems relativity still holds firm.
So while entangled gravitons might have this spooky connection across space, we probably couldn't use them to instantly, I don't know, order pizza from another galaxy?
Probably not. No, the correlation exists, but not a controllable faster-than-light signal.
Right, okay.
Duh.
Now, as exciting as these theoretical possibilities are, the source also kind of hit us with the cold reality, the immense technical challenges we face in even thinking about this.
Absolutely. The gulf between theoretical possibility and actual building something is vast here, especially in fundamental physics.
So what's the biggest hurdle?
The most immediate, the most significant one, as we touched on, and as Rothman and Bone hammered home, is graviton detection.
Still the main problem.
Still the main problem. The incredibly weak interaction with matter means our current tech, and even what we can reasonably imagine in the near future, it just doesn't have the sensitivity.
You used an analogy earlier.
Right, like trying to feel the breath of a butterfly in a hurricane. It's that level of faintness.
Wow. Okay. It really paints a picture of just how elusive these particles are. And, okay, even if we could somehow detect them, the source pointed out the issue of generating a strong enough signal for communication.
Exactly. Think about the gravitational waves we have detected.
Colliding black holes, neutron stars.
Right. Incredibly violent, massive cosmic events. They release truly colossal amounts of energy as gravitational waves, which is why our incredibly sensitive detectors like LIGO can just pick them up.
So generating a communication signal.
Generating and, more importantly, precisely controlling much weaker gravitational signals to encode information. That would be an astronomical undertaking. It would require essentially unprecedented control over space-time itself. We have no idea how to do that.
And then, as if those weren't enough hurdles, the universe itself is apparently quite noisy, gravitationally speaking.
Yes, that's another major issue. The cosmos is just humming with gravitational activity. Constant, subtle fluctuations in space-time from countless sources.
Like background static.
A good analogy. These background gravitational waves, other tiny effects, they would likely just swamp any feeble communication signal we might try to generate or detect.
So you'd need incredible filtering.
Beyond incredible, achieving reliable graviton communication, even theoretically, would need instruments and techniques far, far beyond anything we currently possess just to deal with the noise, let alone generate and detect the signal.
Okay. It really feels like we've hit a wall based on current physics and tech. But the source then went into some truly far-out stuff, didn't it? Almost pure sci-fi, speculating how maybe super advanced civilizations might have cracked this.
Right. This is where we step firmly into highly speculative territory. The source mentioned concepts like warped space-time amplifiers.
I've heard that.
Hypothetical tech, obviously. The idea is maybe you could manipulate space-time curvature itself to somehow amplify or focus gravitational signals, make them detectable over vast distances.
Yeah.
Then there's the even more exotic notion of black hole graviton lasers.
Black hole lasers. Seriously.
Yeah, it conjures up quite an image, doesn't it? Some kind of incredibly powerful focused beam of gravity. We have absolutely no clue how to even begin thinking about building something like that based on known physics.
Sounds like something from a galaxy-spanning epic. And they also brought up graviton transceivers embedded in quantum foam. That sounds like digging really deep.
It is. Quantum foam is this theoretical idea about space-time at the tiniest possible scale, the Planck scale. It suggests space-time isn't smooth down there, but a chaotic, seething mess of quantum fluctuations.
Including graviton?
Including fleeting virtual gravitons, yes. So the idea of tapping into that fundamental level for communication is, well, it's extraordinarily speculative. It relies on advanced theoretical frameworks like string theory or M theory.
The theory's trying to unify everything.
Yeah, actually. They try to describe the stuff even particles are made of, and they offer some mathematical ideas about how gravity might work at those tiny scales where quantum foam might exist. But these theories are still very much under development, no experimental proof yet.
So, deep theory, far future, maybe.
Very far future, if ever. The source even touched on the idea of using controlled graviton fluxes to stabilize artificial wormholes.
Wormholes. Okay, now we are in sci-fi territory.
Yeah.
So the implication isn't just faster communication, but maybe faster travel, too.
Potentially, yes. If you could manipulate gravity at that fundamental quantum level, stabilizing a wormhole might theoretically be possible within some of these frameworks. It's staggering to consider.
Truly. Okay, let's pull back slightly. Let's talk impact. If, and it's a colossal if, but if we could somehow overcome all these massive hurdles and get real-time, maybe even FTL communication via gravitons, what would that actually mean? The source hinted at some huge game-changing implications.
Oh, the implications would be revolutionary, utterly transformative. For one, think about space colonization.
That's so.
Our ability to coordinate it would fundamentally change. Instead of waiting years, decades, for messages between star systems.
The 20,000-year delay.
Right, gone. You could have near instantaneous communication. That allows truly scalable, coordinated interstellar expansion. Imagine managing resources, responding to crises, sharing discoveries across light years in real time. It's a completely different ballgame.
Yeah, coordinating complex science or even just, I don't know, emergency responses across star systems. It would change everything about humanity's future out there.
Absolutely. And the source also raised the intriguing idea of synced machine learning systems, AI operating across interstellar distances.
What would that enable?
Well, picture these vast distributed networks of artificial intelligence spread across multiple star systems, but able to collaborate, share data, learn, all in real time.
Like one giant brain.
Sort of, yeah. It could lead to unprecedented breakthroughs in science, tech, our basic understanding of the universe, far beyond what isolated AI systems could ever achieve. A galaxy-spanning supercomputer with emergent intelligence, perhaps?
Wow, that level of interconnectedness is hard to grasp. And then the source went into some even more philosophical, maybe slightly mystical areas,
Yeah.
hinting consciousness itself might interact with gravity more deeply than we think.
Yeah, this delves into very speculative ground, really pushing the boundaries of current science. The underlying thought is, well, if gravity is so fundamental to space-time structure, and if consciousness is somehow deeply tied into the fabric of reality,
Which is itself a huge philosophical question.
a huge one, yes, then perhaps there's a more direct fundamental link between consciousness and gravity than we currently appreciate. It raises profound metaphysical questions about thought, existence, their place in the cosmos.
It really makes you wonder about fundamental connections we haven't even begun to understand, and the ultimate thought the source left us with, this idea of graviton entanglement, forming a kind of cosmic internet,
Right.
linking not just machines, but maybe even minds, entire civilizations across the universe.
It's a truly awe-inspiring vision, though, again, we have to stress, it remains firmly in the realm of speculation for now. The concept of a fundamental network woven into space-time itself, potentially enabling instant connections across impossible distances. It's a powerful idea to think about.
So as we wrap up this deep dive into the tantalizing potential of graviton communication, we're left with some absolutely enormous questions for you listening. Will this ever move from theory and speculation into reality? Could the weakest force in the universe actually become the strongest link for communication across the cosmos? Or is this just a beautiful, mind-expanding idea that's destined to remain just beyond our reach?
These are precisely the kinds of fundamental questions that drive science, aren't they? They fuel that innate curiosity we have about the universe. And while the challenges we've talked about are clearly immense.
Understatement.
Yes. And the speculative nature of many of these ideas is obvious. That fundamental human desire to understand, to know our place. That will undoubtedly keep pushing the boundaries of what we currently think is possible.
Absolutely. And even if this specific dream, graviton communication, remains distant, just exploring these possibilities deepens our understanding of gravity, quantum mechanics, space-time itself.
Exactly. It serves as a powerful reminder that the universe holds mysteries far, far greater than our current comprehension.
And maybe, just maybe, hidden within those unfathomed mysteries, the weakest force holds the strongest yet to be realized promise for connecting us all across the cosmos.
A future of connection we can only begin to imagine.